phonograph record's been with us a long time. I've been around this business a little longer than most of you have. When I was about your age, there was a thing invented called a tape recorder. And when this happened, they said, well, phonograph records won't be around for much more than about 5 more years. This was about 1950. So by 1955, there won't be any more phonograph records and everything will be on tape. Well, here it is, 1980, and we're still manufacturing a lot of phonograph records, but somebody was wrong in their prediction. But phonograph records have been around a real long time, and I think they'll be staying around even a longer time. And I think it's obvious to you after you've worked with tape, worked with cassettes, and worked with records, how easy records are to handle and store and this sort of thing, and find a selection. You don't have to rewind and search and look. You just pick it up, put the arm down, there it is, and you play it. And another thing, of course, we can manufacture records considerably at a lower cost than you can tapes, although this isn't really reflected in the store. When you go out and pay $7.77 an album, that isn't really reflective in the fact that it costs to have that record manufactured about 75 cents, even today. Maybe even a little less. And maybe, as far as the jacket concerns, $1 a piece for a jacket or $1.25. So there may be $2 invested in that record somewhere along the line, but there's an additional $5.77 that somebody else is making. Well, it goes through a lot of hands, and that's where all of the money is made in the records. Not necessarily what you and I are doing, but the people that are marketing the thing. They might think about that too sometime. Maybe you want to market some of it. But as far as records are concerned, as you all remember, Thomas Edison invented this crazy thing. And he did it in a little different fashion than we do today. He used a cylinder, looked like an overgrown toilet paper cylinder, and he put wax on this thing and turned it and connected it to a horn, looked just like a horn loudspeaker. Only instead of having a loudspeaker at the end of the horn, he put a diaphragm, which would be similar to the loudspeaker diaphragm, and then put a stylus on that diaphragm, which went down into the wax. And he had a motor driving the little cylinder, and another lead screw, we call it, that drove this horn across the wax cylinder. So as he would speak into the cylinder, the vibrations from his voice would go down and be transferred to the little stylus on the end of the diaphragm and vary the pressure in the wax and be moved across, and he could talk for 10 or 15 minutes or however long he wanted to with that thing. And he produced sound. Of course, to play it back, he reversed the process. He simply took the same needle, put it back in the wax cylinder, started the cylinder turning and the lead screw driving it across. And lo and behold, the sound that caused the movement of the stylus and put impressions in the cylinder now moved the diaphragm again. You could hear the thing talk back to you. And this was all done mechanically. There were no electronics involved at all. And for many, many years, there was no electronics. In fact, the first 30 years of phonograph records had no electronics involved. But this didn't work very good. He ran into a big problem with these cylinders. These things that were about this big around, about this long. How in the world are you going to mass produce a thing like that? It's pretty hard to do, to get some kind of a crazy machine that can make these cylinders and put the impressions on them. And some of the French said, well, that Edison's got a good idea, but he hadn't gone far enough with it. He said, I think it would be a lot easier if we took and made this thing into a platter, like a plate. And if we wanted to mass produce those things, we could do it in a great big press, where the press could just turn out these flat plates as fast as we could run them through the press. And lo and behold, they found this way of making the sound impressions. They did it on a flat plate rather than doing it on a cylinder. And I like to think of major things in the recording business as if you want to say the 8 great wonders of recording. This was the first one. The first great wonder of recording was the making of the flat disc, because this now gave us a method of mass producing records at a low cost so the general public could have them. And the disc was the big thing. Of course, Edison even finally changed over to the disc. How many of you have ever seen the Edison phonograph records? They're about a ½ inch thick with a hole that's about a ½ inch hole in the center. You've seen some of them. You ever find them, latch on to it, because there aren't very many of them left anymore, and they're becoming more and more valuable. And the old Edison players, by the way, that player operated the same way in the Edison system, where the motion of the stylus was on the flat plate was like this, up and down, which they called Hill and Dale recording. And the majority of the others at the same time didn't move the stylus up and down. They moved it sideways, a transverse motion of the stylus with respect to the groove. And even some of the people didn't standardize in an early time. There were some of the records that ran at 80 RPM, some that ran at 78, some that ran at 85, and even a few at about 70. So if you wanted to come out with something different at that time, you would simply bring out your own machine, which ran at a different speed. So what the people with the players did, they did the same thing you'd probably do. If it was a little too fast, you put your thumb on it and slow it down. So I said, if we have to do that, why don't we make a variable speed player? One, we've got a lever over here, can vary the speed of it. And they did. A lot of the early record players were variable speed. That way, if you wanted to sing along with it and it wasn't quite in your key, you could vary the speed of the phonograph and put it in your key and sing along with it. Or pitch it to your piano, or whatever you wanted to do, by varying the speed. And the speed finally standardized in the early days at 78. Well, it really isn't 78. It's 78.26 RPM, revolutions per minute. And this became the standard speed for home-type phonograph records until about 1950. And then into the 50s, we got into long play records. The 33 1/3 speed that we use today was used very heavily in the broadcast industry. And they made what they called transcriptions. And the transcriptions were records that were 2 inches larger than this record. They came out this far. The record was that big. And they ran 15 minutes on a side. And the radio shows at that time were recorded. The first half of the half-hour show was on one record and the other half on another record. And in order to make it more economical, you put 2 shows on 2 records. And the majority of the radio shows came out that way. They also did another interesting thing on many of those, because there was a frequency response different from the inside of the record to the outside. The outside of the record had better high frequency response than the inside of the record did. What they would do is record the first half of the radio program from the outside to the inside. The second half was recorded from the inside out. In other words, you put the arm down on the inside and played out to the end of the record, to the outer diameter of the record. And then that was the end of the program. The reason this was done is so there was not an apparent audio shift of audio quality when you switched from one record to the other, and the program would sound continuous. In fact, I know you've all worked with tape recorders. The primary reason the Germans invented tape recorders was to get away from this problem. Adolf Hitler was kind of a slippery guy. He knew there was people out trying to get him. Even his own generals trying to kill him back at that time. And he wanted to fool the people. Even the Allied bombers were coming over and trying to bomb him wherever he was. So what he did, he commissioned some of his scientists to develop a recording system that wasn't like the disc records of that day. It was so good that they couldn't tell it was recorded. So they developed a tape recording system. Hitler would record his speeches on this tape. They would tell the public where he was, but that isn't where he was. He was someplace else. Of course, they knew he had been there because the broadcast normally emanated from that place. That's where he did his broadcasting from, but he was not at the studio. He was somewhere else. It was coming off of tape. So they got the jump on the rest of the world as far as tape was concerned. And as you'll find out a little later, the advance of tape and what tape did for us forced us to improve phonograph records. Phonograph records had stayed pretty well static from about 1929 through the war until about 1950. Nothing had really been done. We hadn't improved anything. But now we have to get into some of the things that we're concerned about in making phonograph records. As long as it's a mono phonograph record, the type that you were probably had seen when you were real little. And, no, you're all old enough. You weren't around when there weren't stereo records. Had to. But in mono records, the stylus motion on the record is all in this direction with respect to the record. But in a stereo record, we run into a different problem, and that problem is when you're transferring a tape to a record, you have 2 tracks on the tape. Well, you might say, well, how do you do this in the groove? Well, this information from track A and track B that you mix down in the mix down room one goes into one side of the groove and one goes into the other in a fashion like this, where looking at the groove, if we were taking a cross cut, slice across this record, we would see something look like this, and greatly magnifying the groove. In a mono record, the groove would simply move like this, and of course back and forth in this direction. There would be no change in the depth of the record. In a stereo record, we get into a different situation. And it's still, I'm sure, not immediately obvious why there could be a problem, but there are many that can come up. If we wanted to show the information in the right channel, what we'll do now is move this groove in this fashion. We've taken this wall and moved this up and not affected this wall at all. This is all right channel information. So now the groove really, since of course this doesn't happen, looks like this. Right here. And of course this is gone, disappeared. Now the groove looks like that for that period of time that the right hand information is modulating the groove. Now we could also have a condition where we might have the left hand groove moved over. And if the right and left hand would move in the right phase relationship, the groove gets smaller and smaller. This would move over to here. This could be moved over to here. Now, that could keep going to the point where the groove would disappear, depending upon how loud the left and right channels were, and that can happen. That would normally happen with an out-of-phase condition. When you mix something, particularly when you're mixing, your instructor would tell you, now keep the kick bass in the center and keep your bass pretty well centered. The reason he's doing that is so that the bass information now causes this type motion. If the bass is out of phase, in other words, when one speaker's moving out, the other's moving back, and it would appear to be very wide split rather than being centered when you listen to it, the groove would move this direction. It gives you no problem as far as the tape is concerned. But when you're going to make the record, what's going to happen? The needle is going to be doing this and go up, off, and leave the record. Well, you can't play it when there's no groove in the record. So that's where the problem occurs. Well, you might say, what frequencies, where does this happen? Does it happen in the treble? Does it happen in the bass? You must happen in the bass, because that's all he's been talking about, the bass. It must have something to do with the bass. And you're right, it does. Happens in the bass. If we were to look at the frequencies from 20 cycles to someplace up around 20,000, we've come into a standard in phonograph records that have developed over years and years, and this didn't happen overnight. It really didn't happen until the 50s, that we really standardized things. Things were done differently. They found that if we feed the cutting head with the same power from the amplifier, in other words, you put 5 watts into the cutting head at 20,000 cycles and at 20 cycles, we'll get a funny thing that looks like this. The motion of the stylus, how far it moves, looks like this. So as we go down in frequency, let's call this displacement. That's a big fancy term for how far it moves. That's like how much water does a boat displace when you put one person in or 5 people in the boat. Displaces more water, so the displacement's greater. But what we're saying here is that as you go down in frequency, feeding the cutter head with the same power at all frequencies. We put a power meter on here and turn the oscillator to 100 cycles, and then turn the oscillator to 1,000 cycles and make it read 5 watts at all frequencies. The movement of the cutting stylus looks like this. It gets greater and greater as we go down in frequency. Well, that's going to cause a problem. This means if we want to cut the low frequencies, feeding the head with the same power at all frequencies, we're going to have to move the grooves way apart so that this great big swing of the groove won't cut over into the next groove. Because if it cuts over into the next groove, it's going to skip, and we can't play there. Well, maybe we need some other system. Maybe we have to go to a system where we would keep up to a certain place the displacement constant. We try to keep this amount that the stylus moves up to a certain frequency the same. Let's take that to 1,000 cycles, for instance. That's a good, we do everything's around 1,000 cycles. You ever wonder why? why everything's based around 1,000. Why don't they use 5,000? Why don't they use 3? Well, you look at the amount of spectrum as far as the number of octaves between here and here, and they're about the same. So as far as musical octaves, you're about the same. This is balanced from here to here, not in total frequency in hertz, but in the number of octaves, it's balanced. Well, we'll keep it constant displacement. This means now that if we're going to keep displacement constant, we can't feed in the same power. Here's our displacements. Okay, we said that if we fed the same power in to the cutter head, it was going to get greater and greater in displacement and went down in frequency. That means that the cutter head power has to drop off. So this means what we have to do. We're going to have to design an equalizer now that will reduce the bass that's fed to the cutter head. Because if we don't, we're going to exceed the amount of movement we can allow the stylus to have on grooving the record. So we've done a thing like this. Now we've said we've got an equalizer. If we have done that, when we record it, what do we have to do when we play it back? Yeah, we've got to compensate. We've got to put in another equalizer, don't we? So what we have to do is, this is for playback. What we've got to do is a thing that looks like that. The playback then has to be boosted in the low end. Have you ever fed a microphone, maybe you've done this, through your phono input on your preamp and listened to the audio quality on it? You can try this sometime. Many of your preamps have a spatial position and this sort of thing where you can feed a microphone through on the preamp, switch it over to the phono position, and suddenly it'll become very bassy sounding. That's because of this. That's that equalizer that's built in that compensates for the fact to keep constant displacement of the cutting stylus on the record. We reduce the power that's fed to the cutter head in this fashion. Now, what we could do from that point on might just be a straight, we could feed the same power, because above 1,000 cycle displacement doesn't bother us. But there's another thing that bothers us above 1,000 cycle on a phonograph record, and you've all heard it. Have you ever played your phonograph through without a roll-off on the high end? What do you hear?
Pops and cracks.
Pops and cracks and all sorts of noises, don't you? That's the big problem you get above 1,000 cycles, is not the overcut, but the noise problem. You get hiss and pops and vinyl noise and molding noise, and everything comes through. So what we would really like to do someplace up above 1,000 cycles is roll off the high end so that we could reduce these pops and cracks that come through the record. But if we do that, what we have to do when we record it is boost it. So again, we get a thing that looks like this. This is that's the power of the cutter, and this is your playback amp. So what we end up doing above the 1,000 cycle region is again boosting the frequencies above 1,000 cycles, and this boost is at the point so that at 10 kilohertz, the total frequency boost is about 13 3/4 of a dB. That turned out to be the RIAA frequency. This cut is such that at 100 cycles, it's also about the same thing. It's right at 14 dB. You're right at 14 dB down at 100 cycles. And this later came to be the RIAA, the recording industry standard that you all know of today. We're very fortunate. When I was your age and we had lots of phonograph records, every manufacturer had a different curve. Columbia had one, CBS had one, or RCA had one, His Master's Voice out of England had one, Decca had one, Mercury had another. They were all different. So this meant on the front of our preamp, we had to have a switch that read RCA, CBS, Mercury, HMV, all these positions to make the record sound right. But very fortunately, in the 50s, they got together and decided on this curve, which today is the RIAA curve. And all of us, including the Europeans and Russians, everyone that cuts records, does it this way today. One thing we've been successful in, we haven't been that successful in some other thing. But that is really how the curve was derived. Yeah. Okay, what we do in the high end, we run a boost in the high end in order, when we boost the high end of the record, this means that in order for you to play it back, sound properly, you have to roll it off. At the same time you're rolling off to compensate for what we did when we recorded it, you're rolling off the noise. So what has happened at 10 kilohertz, the noise is reduced by 13 3/4 of a dB over what it would have been if we recorded it without the boost. Now the same thing is true in your FM receiver. In fact, the curve is almost identical in your FM receiver. The output of the little circuit in there that detects the audio signal off the RF goes through a filter that does the same thing, because there is FM noise. This means that the FM station does this. They don't do the same thing in the low end. There's no reason for it. But they do almost an identical thing in the high end. Now this probably doesn't immediately suggest any problems to you, but we're going to talk about some of the problems that this creates. How many of you have ever listened to phonograph records where the drums, particularly crash cymbals, so it didn't sound like crash cymbals, but shattered glass when they hit it? You ever hear this? You may have even heard the same thing on tapes. How often have you ever heard it over an FM station where they get a good hot rock record on, and the high end, particularly hi-hat, cymbals, even the S's, the sibilants from the singers, sound like shattered glass whenever they hit it? It almost sounds like breaking up real bad. Well, it is, because this creates another problem when you do this boost. And we'll get into that and see what it is. But FM has the same problem. So they go through some very fancy pieces of equipment. How many of you have been in an FM station? Been around radio at all? You'll find someplace before you get to the transmitter a couple little fancy boxes there made by Orban or CBS or somebody. And this box does nothing more than control this thing so it doesn't come out sounding like shattered glass, you hope. And makes controls on this thing. But that's really what the recording curve is. And that's the curve that we use today, the RIA curve. And that's about what it looks like. Any questions on that before we go romping off into something else? But that's what we call the recording curve. And this is really the curve that is fed to the cutter. It looks like this. That one right there. You play back with this curve that looks like this. And hopefully, if everything is adjusted properly, it all comes out flat. Which isn't always the case. Yes. Recording Industries Association of America. And this was really a merger of the companies, where the CBS and RCA, and it is really the closest to the audio engineering. You've all heard of the Audio Engineering Society, I expect. The Audio Engineering Society came up with a curve in about 1953 or 4, about that time. And when they did, this was the one that it's slightly different than this, but it's so close. And that was the group that really brought everybody together. They haven't been that successful on tape, but they did it. And the Recording Industry Association of America finally got together and said, this is the way we're going to do it. And we've all been doing it that way ever since. Makes life a lot simpler. Now, I mentioned to you earlier that there was a problem as far as frequency response and diameters and this sort of thing. And we really don't worry too much about it today. We did a long time ago. We don't today. And in 1951, been almost 30 years ago now, a fellow up at Fairchild in New York found that if he took the cutting stylus, the cutting stylus looks about like this. It does not look like your little playback stylus in your phonograph. It looks more like a cutting tool or something you'd use to plow with. That's really what it's doing, it's plowing. The side, looking in on the stylus with the record moving this direction would look like this. If you were to look at the side view of it, it looks about like this. With the record moving this direction here, and the record moving in this direction as we're looking at it here. he found that if he were to down here wrap this thing with nichrome wire, the type wire that's used on heating elements for your hair dryer, he could heat this thing up, and he found that if he heated it up, the noise on the record reduced dramatically. In fact, almost 20 dB, maybe even 30 dB at times. He could vastly reduce the noise on the record. He also found that if he did that, in those of you that have ever worked with any cutting tools, most of you probably haven't, but they'll put a slight reduction of the sharpness where it's very, very sharp in cutting, and they call this burnishing it, so that it'll cut the work you're doing a little smoother. He found that this burnish, which was very necessary on the styluses without the heat, could almost be removed. He didn't need any of it, so he could have a very, very sharp surface here as far as cutting the record. And by this technique, he could cut the full record and didn't have this loss of high frequencies as he went towards the inner diameters. And this technique is used by everyone today. And of course, back at that time, it was called hot stylus. And unless you had it, you weren't on the in group as far as cutting records. So that's the only way you could do it. And it's done very simply by wrapping a nichrome piece of wire around the stylus. Normally a cement, very similar to the cement that's used to hold a spark plug together for your car, which will withstand temperature, is used to cement that thing on. It doesn't have to be cemented. It can be done without it. But this was done about 1951. And that was another major advance in the quality of phonograph records. See, one thing was pushing this, tape was coming along about this time. But now, with this, we could previously cut a record that had the noise down about 50 dB from the peak level on the record. With this, we could reduce it down to the noise of the turntable itself, which should be down another 25. So now we're talking about noise that is down in the neighborhood of 75 dB. Well, the tape at that time was 50. So the people with the phonograph records had made a major advance over the tape people. Had 25 dB on. Well, of course, in addition, we had stopped using shellac for phonograph records. You've all seen the old 78 records that had a piece of paper in the center. And of course, if you hit it on something, it'll break. Now, that record was made of shellac. It's a hard shellac, very similar to the shellac you'd use on wood, except it was made to harden. And it was baked that way. And it was very brittle and break, and also very noisy. And also about this same time, it came up with the use of vinyl, which was a petroleum derivative plastic that was pressable and very, very, very accurately pressable as far as phonograph records are concerned. So they ended up using this form of a plastic that greatly improved. And we ended up getting pressed records that were far, far better than anything we had in the late 40s in the early 50s. And that was a major advance in phonograph records. So this was one thing that kept phonograph records from dying in the early days. Then, about this same time in the early 50s, they found that they didn't have to put just 3 minutes on a 10-inch record. They could go to what they called a fine groove technique, micro groove technique. And with this technique, they could put 15 minutes on one side of a 10-inch record. Before, they only had 3 minutes on there. So we went, because the noise had been reduced, we had a much better surface, a much better quality record. We get much longer running time on it. And this is when the advent of the 33 1/3 came back into play. The long play record, of course, wasn't a necessity any longer to run it at 78. You didn't need to. So the old 33 1/3 broadcast standard was used as the standard speed for long play records. And this was very successful. CBS came out with the first long play records, and the thing immediately caught on. Well, a person would be willing to pay twice or 3 times for the record if they could get a very high quality record, one that didn't have all the pops and clicks and cracks on it from the surface noise, and also get more playing time. So the first introduction of long play record was on 10-inch and caught on very well. In fact, it caught on so well that RCA was a little late in the ball game, and they said, well, we've got to get caught up here. They had tried to introduce 12-inch long play records in the 1930s, but due to the Depression, it flopped. And RCA finally went back into the archives, dug out some of their 33 1/3 material, and said, well, why don't we do them one up? We'll make a 12-inch 33 1/3 while they're making the 10-inch 33 1/3. Well, RCA jumped in and started making 12-inch long play records. Well, they could get 20 to 25 minutes on a side where Columbia was getting 15 minutes a side. And they had to jump on Columbia at that time. Well, today you see very few 10-inch long play records. Most of them are 12-inch. In fact, you even see some 12-inch disco records today. But everything went to 12-inch, and 10-inch pretty well dropped out of the whole act. But then, in the middle 1950s, we got another thing thrown at us. One of the most successful marketing ventures I think I've ever seen. RCA Institute made a study of phonograph records. And they came out with a paper that said that the optimum phonograph record for a single is a 7-inch record, and it runs at 45 RPM and has a hole like this, a big hole in it. Well, there was no player that existed would play it. But RCA said, we're going to build and market this thing. So they did. They started manufacturing the records. At the same time, they made a player that would play these big records, since none of the existing players would run it. And what they did, they sold you a stack of records about like this and the player for $12.95. What a better way to get the public, cram it right down their throat. You essentially give them the player, you know. But in order to get more records for it, you got to buy RCA 45s. Nobody else had it. And this is the way the 45 record started. Started by RCA cramming it right down the public's throats. The public was happy about it. And everybody was buying 45. Of course, a lot cheaper than LPs. But this was in the middle of the 50s that happened. And we were still, everything was mono at this time. It had not gone stereo yet. Well, you might say, why didn't we have stereo? Well, the very technique that we talked about, the way we moved the cutting stylus, moved the sides of the groove to produce the stereo, the left and right stereo, was invented in 1931, but didn't catch on. In fact, the patent still exists. The original patent was issued to a fellow by the name of Blumlein, and he lived in England. But everybody said it won't work. It's no good. Nobody wants to buy a stereo record. And in fact, in the 1955, it was, one of the companies on the East Coast, Cook Records, you've probably even seen them today, some of the old Cook, they were some of the best records you could buy, had a fantastic idea how to make a stereo record. What he was going to do, since he didn't like this particular idea of using the left and right side of the grooves, he was actually going to make 2 grooves in the record. So what he did was made one of the first stereo records, and there probably still a few around if you can ever find one of them. They're collector's items today. What he did it like this. The record looked like this. This is the label, this center hole. This is the left track, and this is the right track. And what you end up with is a playback arm that looks like this. It had 2 styluses on it and 2 heads. One head played the left track, and one head played the right track. And you played them at the same time. That meant you cut it with 2 heads, but he had 2 sets of grooves, one for the left track and one for the right track. And it worked. And it sounded pretty good. But this meant now you had half the time on the record. Cut your time in half, because you had to dedicate half of this record for the right-hand side and half for the left-hand side. Well, that sort of didn't go. People didn't buy that very well. It wasn't compatible with what you already had. You couldn't play it on a mono player anyway. No way to do it. So the old 1931 patent was dug out, and Westrex, that's the old Western Electric Company. When you look at the movies and down there in the old black and white movies, you'll see the credit that says Sound by Western Electric. Then the newer ones will say Sound, LI, Westrex, Litton Industries, Westrex. Well, Westrex, that company, is commissioned to build a cutter head that would work on this 45, we call it, principle, where this cutting stylus now was going to be moved, rather than moved as it was in the mono record, would be moved like this and like this for the respective left and right tracks. And we needed a cutter head that could force the stylus into those motions. We didn't have one. And Westrex did. And the first stereo records came out in 1957. That's just a little over 20 years ago that we had stereo records. So any of you that are over 25 or older, they didn't have stereo records when you were born. Those of you that are just right at 20, you're about the same age as stereo records. That's as long as it's been, really. And of course, that immediately caught on. This thing was fantastic because now you could simply modify your little record player at home. In fact, you could even play the stereo records on it. It didn't do the records any good, but you could play them on your stereo player because it was a compatible, quotes, compatible system. The motion of this groove that was cut by this could also be played on a mono player. And we ended up having a system that worked out pretty well. And of course, the system that exists today. But it was not a new system, it was an older system. That's the way we do it today, even now. We're cutting the record 45-45. And this was 45-45 because of the angle that exists here. This is the groove angle at this point at 90 degrees. And the 45-45 was that we move this side of the groove or this side of the groove depending on whether it's left or right information. Now, if it's mono information, where it's in phase and sounds to you like it's right square between the speakers, the stylus moves in this direction. For the sound appearing anywhere else, it is a motion that involves some vertical motion of one of the walls, depending on where it is. But mono information, in fact, if we're going to make a mono record, we still do this for voice things. It's sort of foolish to cut a voice in stereo. It doesn't mean much. What we do to make the record is simply feed the left and right hand amplifiers with exactly the same signal. We end up with a mono motionless stylus. And that's the way it's done. But that's really how it's done today. Any questions on this before we keep roaring on down the track here? Yeah. Well, there were two systems that were developed, really. It was the SQ system, which involved phasing information, encoding the information, then withdrawing the encoding. And another was to put on a subcarrier. And then the subcarrier is recorded, and then the information retrieved from the subcarrier. The subcarrier, I would liken to you as the sound for television. It's sent along with it, and then you use a separate circuit to pull it out away from the picture. And we did a similar thing here. We sent the back tracks as subcarriers and then simply withdrew them. It was a very difficult thing to work with and has since pretty well died. This was again a case where CBS and RCA would not get together. RCA had the subcarrier system. CBS had the SQ system, which was a encoding system. The advantage of the CBS system, it was relatively compatible. The stereo that you listen to, when you listen to it on a standard stereo system, was not as good. You only had about 8 and 9 dB separation between left and right. And they went through some very, very fancy electronics to try to improve it and this sort of thing. But the whole thing was doomed to failure because they wouldn't standardize. If both companies had come together on a single system, in my opinion, some form of the SQ system would have been the best. In fact, Dr. Lackey and I hold a patent on a 3-channel system that is an encoding system similar to the SQ system, but has better separation and is also stereo compatible because we've got 12 dB rather than 8 dB of separation without any enhancing devices. And we've demonstrated it at the Audio Engineering Society and this sort of thing. Our 3-channel, what we call call it TROD, or whatever, is unique that the encoder and decoder can be built for about $25 a piece. Very, very inexpensive to build. And worked quite well. But you use 3 speakers rather than 4. But then we get into the problem of most rooms are designed for 4 speakers, not 3. You end up having to have one by the door usually or something like this. So it's a little bit of a problem as far as aesthetics and actual useful placement and so forth. But the quad system is pretty well dropped out even on tape. I think that you don't buy really it really doesn't do nearly for you what stereo had done. Stereo had done quite a bit more. I was talking a little bit about the cutter head. Thought I might tell you just a little bit about it, how they work. The head itself is a precision piece of equipment and becoming more and more expensive every day. Just the head alone. We bought the head we're using now in 1974, I think the present head we have. At that time, it cost us $3,800, and I think it's around $7,000 or $8,000 now. It's the same thing. This is just the device that cuts the record, nothing else. The way this thing is built, it is built by connecting to the stylus somewhere, depending on who you have, with a thing that looks like this. So up here, all we have is some coils of wire. And up here, a large magnet. It looks very similar to a loudspeaker, and it is. We also have sets of coils that are wound down lower. These are called feedback coils. If you look at the book, the recording book that you have, textbook, it gives a pretty good picture and description of this thing. But the feedback coils, what I wanted to mention to you, are set to sense the motion of the stylus. And rather than damping like we do in a loudspeaker by putting a whole lot of fiberglass inside the loudspeaker or using some sort of a dead air column to damp the speaker to take out the resonances, when the speaker sounds real hard, got to take those out. Well, the cutter head has the same thing. It has a frequency that it naturally wants to oscillate at or wants to really put out the power at. And this is around 1,000 cycles again, 1 kilohertz. So in order to get rid of that problem, what we do is rather than damping it very heavily, like you do in a loudspeaker in many cases, we'll feed the signal back from the motion out of phase. So it's an inverse feedback, negative feedback like you have around a solid state amplifier, where you put a whole lot of the signal that comes out of the amplifier back into the amplifier out of phase, which has a tendency of reducing the gain of the amplifier. Doesn't squeal or holler because it's going back out of phase. And this feedback then is used to control this resonance. And that is the primary adjustment. If you were adjusting the amplifier, what you would do is adjust the feedback till you pull this resonance down where it didn't cause a problem in the response of the cutter head. This feedback is in the neighborhood of 28 to 29 decibels around most of either the Neumann cutter head, the German cutter head, or the Westrex head. They both take about the same amount. And any amplifier could be used to drive a cutter head as long as it's a good, stable amplifier. DC 300s, you're familiar with. 150s are even used in some cases, the crown amplifiers. But any of those, that type of amplifier, good quality amplifier, can be used to drive the cutter head. And you could build electronics ahead of it. We might say, why do you, I know you've all looked at costs on disc cutting systems and been appalled at the price. When you see a Neumann, the German-made, fully automated system, everything on it, we'll talk about the automation. It's right now about $300,000 for the cutting system. Now for a lathe and the amplifiers and associated electronics that we'll talk about, we're not talking about a figure quite that big. Without the computer, you can probably do about the same thing for about $75,000. Considerably less money, but it's still a lot of money. Now, what's in this chain? Where's all this money go? Well, we're going to show you a tape after a while that shows a picture that one of our engineers made there at our chain. First time he ever run television camera, he did a pretty good job. What happened? How does it get from the tape that you made? Okay, you've all mixed out tape. We're now going to put this on a phonograph record. What has to happen? And what happens if something is wrong? Like I said, if you get too much vertical excursion, it's going to go off the record. How can we stop that? Well, someplace you'll bring me the tape, put the tape up, and we'll monitor it, and and listen to it, watch some indicators and things. But the first thing we have is the tape that you mixed. You have it on a tape recorder. Now, what we'll do first is feed that to a device we call a crossover device. And this is nothing more than a fairly simple audio filter that allows you to feed the signals below a given frequency to both left and right channels. In other words, I could say that in your mix, you had some problem with the toms, and the toms were causing some out of phase that's going to limit the level of record. And however, if I cross that sound over, most of the sound in the tom is low frequency. And if I crossed it over, let's say at 200 hertz, all this problem is below 200 hertz. So what I do, feed it through an electronics that can now cross over and feed the same signals to left and right below 200 hertz. Everything above 200 hertz is fed normal stereo, the way you mixed it. Just we disable it. What we normally do is if the tape is noise reduced, we'll go through either DBX most of the time or Dolby. More DBX than Dolby, I think. And return it back to its original configuration. This sometimes can be put in ahead of the crossover or can be put after. It doesn't really make a whole lot of difference. Now, from that point, going through the noise reduction, decoding is a very common problem. That the sibilance from the voice or particularly muted trumpets or cymbals can be too hot. Where you remember we said this curve went up like this. And if we try to record it that way, when you go to play it back, it's going to sound like shattered glass when it hits that cymbal, or that trumpet sounds like he's playing it through a broken glass. We can go through an equalizer where we can, either in third octaves or in octaves, control the frequency response, just like you are when you're mixing. From the equalizer, we could also, at this point, if necessary, add reverb, whatever. You want reverberation. If we bring a dry tape in out of the field that somebody's recorded on location, they may want to add reverberation and make it sound a little fuller and a little cleaner. Or any other effects. You might want to do some doubling effects, or you might want to add the harmonizer and a reverberator, this sort of thing to make it sound big. Yeah.
How often do you do that, Phil? A lot.
Yeah, for things to record, we do a lot of work for schools. Where if they recorded in the school auditorium or recorded outside somewhere in the room.
An engineer with mixed sound in a big studio, you wouldn't have to know.
Not normally, no. But all this has to be available in the chain so you can do it if you need to. From that point on, what we'll do, a lot of fellows don't like to mix with limiters. And we'll have a pair of stereo limiters. The stereo limiters are on there for two reasons. One, to keep from causing the record to be driven to the point where it could overcut. And another thing, this increases the overall level of the record. The big thing in records for many years was see who can make the loudest record. We really don't care how the tape you made sounded. We want to make your record sound louder than the other guy's record when he played back on the phonograph. Well, we're getting away from that a little bit now. I'm getting more back to making a quality sound rather than see who makes the thing sound the loudest. That game's over. So we go into stereo limiter. Now, in order to remove other problems that might occur, supposing you did let a cymbal get out of hand, even though it was done in the studio. We have what we call a high frequency limiter. And this does nothing more than affect the frequency above 5,000 cycles. And is what we call a hard limiter or an instantaneous limiter. One that acts immediately and then recovers immediately. And when you worked in the studio and you've had somebody's voice to the limiter, you've noticed that the limiter limits quickly, but it takes a little time for the limiter to turn back on again, to bring the gain up, which is the release time of the limiter. The attack time is how fast it shut down, and the release time, how slow it turned back on. This thing turns off instantaneously and back on instantaneous, practically. But you might say, if it's going to do that, it's going to distort the waveform. Well, it can, but the harmonics produced by the distortion above the audible range, so it doesn't really bother you. This will take care of sibilants and cymbals, muted trumpets, this sort of thing that are excessive, where there's too much energy up in this high frequency and it's going to cause distortion, not so much in the recording, but when you're going to play it back. From the high frequency limiter, then we can usually go to the cutter amp. Most of these amps are at least 100 watts a channel, some of them 200, depending on the cutter head we're driving. The Westrex head and the Neumann head at 1,000 cycles take less than 1 watt to drive them. But then you say, why in the world would you use a 200 watt amp? And I said, well, before they were using DC 300s, which are 150 watts a side, and most of the manufacturers don't use anything less than 100. Why would you need a 200 watt amp or a 100 watt amp to drive a cutter head that only takes 1 watt? It makes no sense at all, does it? But wait a minute. We said that when we were recording the high frequencies, we're going to boost them. And supposing I had a frequency from a drum or a voice, sibilance in a voice, where the power at 10,000 cycles was the same as it was at 1,000. Where that sibilance was very, very strong, or the cymbal sound was very strong. Now we're talking about we need 1 watt at 1,000 cycles. How many watts in the amplifier do we need for 13 dB? Say, it takes 20 times. For it to be undistorted, we have to have an amplifier capable of producing 20 watts. Supposing going up to 15,000 cycles, this curve keeps on going up. At 15,000 cycles, we need 17 dB. This means 17 dB is 50 times. If that same power exists at 15,000 cycles, it existed at 1,000 cycles, we need an amplifier capable of 50 watts. Now, that's for the average. Supposing our peak power is 3 times that. Our peak power is not 1 watt, but 3 watts. That means we need an amplifier capable of 3 watts upper level to handle it, and 50 times that is 150 watts at 15,000 cycles. This is the reason for the big amplifiers and cutting system. We may only need 3 watts at 3,000 to handle the peak, but we need 150 watts at 15,000 to handle that peak power, which may only occur for a very short instant of time, but we need that sort of power to handle the peaks at the high frequency, and that's the only reason. We don't need it in the low end because we've rolled the low end off, remember? The low end's reduced. We need it for the high frequency. And now, supposing we try to record those things in the high frequency, what happens? Well, you can see why we've got limiters here. Let's see what's going to happen in playback. I think I mentioned before, and it may not have been obvious. You may say, well, that's just a mastering engineer talking. He can make a record that nobody can play because the things can happen on the record, you can't play it. That is right. You can make a record that you can't play. Doesn't make sense, does it? There are 2 types of distortion that occur in the high frequencies. Well, if you were to look at the motion of the groove has a certain velocity. It's like a speed at which it's moving. Okay, it's like your car moving down the road. Only the stylus, the playback is fixed and the road moving. It's relative. And this velocity has another interesting thing that occurs. As you move farther and farther into the record, it does what? Slows down. It's not as fast. You're not moving by as fast as you were on the outside of the record. So distortion can occur And remember, we said the stylus is moving across the record, transverse to it. When the velocity of the stylus, the speed at which the stylus is moving, equals the speed of the motion of the phonograph groove itself. When these two are equal, we begin to get into a case where we have what we call velocity distortion. This means now that your playback stylus doesn't want to follow it. It has a tendency to want to ride up on it, ride up in the groove, because it's being forced up by this increased velocity. And as you might suspect, this problem is worse and worse as you move in.
Usually, where's the office located?
All right, I think you can wind right back through here. And yeah.
Is that like a tracking error?
You betcha.
Is that the
It's showing up that way. It'll show up and sound very similar to tracking error. In fact, on a record, we call it intergroove distortion. And we have to be careful not to let this occur, it's more of a problem on the inside of the groove because its velocity is lower. So how many of you have ever tried this experiment where you've listened to the outside groove and then listened to the inside groove and could hear this effect occurring? Have you ever heard it? Now we've talked about it, I'm sure you'll try it sometime. Just take any record you've got, anything you've got there, and especially if it's good and hot, good hot record, and do this. Play the outside groove and then lift it up and put it on the inside. If you've got tracking error, it's going to be magnified, but it'll show up as intergroove distortion. This is one type of distortion that we can get into. And what we have to do is look at the phonograph record. You know, we said that if we look from the 20 cycle low up 20K, we don't have to worry about anything below 1K. That's right in the center. We forget about all that stuff below 1K. The only type of distortion we get down there if we cut the groove too big and cut over into the next groove. And skip, you've heard records skip, where you get the right combination of groove geometry, you can make the thing jump over to the next groove. You may put it on another player, it won't. Depends on how good you're tracking and everything. That distortion is displacement distortion. We've talked about that. But we find that what we would have to do for different types of record is limit these frequencies, how much power we can put in the groove, how far we can actually allow this velocity to go. And then above, we get into another distortion. And this is what I call acceleration distortion, and some people call it curvature distortion. It's caused by the high frequency trying to make the stylus move too fast. This is trying to make it move off of it, that increase the velocity. This is real high level material. But the increase in acceleration is from the frequencies involved, frequencies and the amount of power. Above about 5K, it begins to get to be a problem. From 1K to 5K, we're concerned primarily with velocity distortion. Above 5,000 cycles, we're concerned about acceleration distortion. And that is really what the high frequency limiter, the one that we had over here, this thing that controlled high frequencies, just stops that from happening, the acceleration from happening, because if it does above 5,000 cycles, it turns the frequency response like that for an instant. When that is there and it's told that there's too many high frequencies here. It said, okay, chunk, I shut them down and then turn it right back on. In fact, the better ones do it in two bands. One band that goes from 5 to 10, and another from 10 on up, 10 through 20. They break it into those two octaves. This is, of course, quite an octave, but they break it that way. You shut it down in this region or this region, depending on where it's told to be shut down, so it won't affect your ear as much. And it's difficult to hear that this is being done unless you can hear the material before and after. So you can hear the before and after, you can tell. You can tell it's been chopped off. But to hear it afterwards, it's a little difficult to tell. But this keeps from causing distortion in your phone. We say, how does my turntable distort? Why is it going to distort up in this frequency range? Well, what happens is that the groove looks like this. At very, very high frequency. And if the radius That's the radius of this groove right here is less than the radius of the stylus. It can't follow it. It just forces it right up out of the groove and then back down. It can't play it when this radius is less than the radius of the stylus. So to get around this, they've come up with elliptical stylus. Most of you probably use that today. Originally, the stylus didn't look that way. And you can see it's real obvious why we went that direction. When we used a conical stylus, you can see it was much more of a problem. This happened much sooner than it did if we could shape the stylus like this. So an elliptical stylus gets around this type of distortion, which is acceleration distortion or curvature distortion in the high frequencies. In fact, but that brought on a new problem, somewhat of a problem. When you're playing a phonograph record, looking at the groove again expanded, your stylus comes down and looks like this and contacts the groove there and there. Well, we're talking about big accelerations where the thing is being moved very rapidly. But this has to force your playback stylus to move, okay? And if the playback stylus doesn't want to move, makes resistance, something's going to give. And you're going to knock off probably little pieces of the record. But every time you play it, you knock off a little piece where this is very, very loud. And after playing it 25 or 30 times, suddenly it sounds fuzzy where you have these loud passages. They are no longer clear and crisp. They begin to sound fuzzy. And the longer you're around, the fuzzier it gets because you've knocked these edges off here. And that's because of the very, very high pressures right here. We went through an exercise. I don't remember whether the number's in here or not. I could tell you how high that pressure really is. Yes, it is. For one case, this was done at a frequency of 10,000 cycles for a velocity of 25 centimeters per second using a conical stylus, which would have a point of contact similar to an elliptical. We ended up with a pressure. The pressure right here was about, well, it's roughly 5 times, well, let's put the zeros in. That makes it a little more impressive. 1, 2, 3, 4, 50,000 pounds per square inch equivalent. It's fantastic. 50,000 pounds per square inch equivalent pressure right there. So you can see why the records get knocked apart. And with either the conical or the elliptical stylus, this is true. The Japanese said, let's find a way to get around this. We can't live with that, and they did. The Japanese have a good system. They come up with what they call a Shibata stylus. The Shibata stylus was designed so that when the jewel that rides the record did something like this, rather than having a point at which it contacted the stylus, the groove, it contacted over this total area, where they now expanded the area of contact by 10 times. That meant that this pressure was reduced. Rather than 50,000 pounds per inch, it was 5,000 pounds per square inch pressure, which was a dramatic reduction. And the Shibata stylus was designed primarily for the CD4 records, because the CD4, as we mentioned, recorded some very high frequency subcarriers on it. And if you played that with a standard, good, high quality elliptical phonograph, after 4 plays, it was ruined. And of course, you couldn't live with that. So the Shibata stylus was designed, because the CD4 system was worked in conjunction with the Japanese, to come up with a stylus that would produce a much longer groove life. Yeah.
How does the stylus separate left and right channels?
Well, you have a thing on your playback, if you were to look at it, looks very similar. The stylus is either being moved this direction, which resolves the direction this way. You could put a coil up here and move this coil in and out of a magnet and then pick the voltage up off the coil, or you could move a magnet and keep the coil fixed. This would sense this motion. You'd have another coil over here, or a moving magnet or a moving coil. They'd make them both ways. Most of them are magnetic, and it would sense this direction. See, when you're moving this way, this one doesn't move. And when you're moving in this direction, this one has no resulting motion. So that's tied to the shaft some way. It's through cantilevers, this sort of thing, but essentially it's tied in there. And that's the way you generate left and right hand voltages. And that's really the way you do it today. And there's a controversy today as to whether the moving coil, and those of you that are hi-fi nuts, I know have a preference that you're either moving coil or you're moving magnet. And most of the super ones are moving coils. So, well, the cutter heads that make them are moving coil. If that is any consolation or helps strengthen your position. It's helping. Anyway, but that's the way it's pretty well done today. Any questions on any of this? We've gone through an awful lot of material. Yeah.
How about something like this?
Oh, there's a lot of ways to do it. You realize, of course, when you'll see the pictures of the cutting mechanism. The cutting mechanism that makes the record is on a swing arm like this. It moves straight across the record. When you play it back, you have a pivot point. You swing about that pivot point, normally with something that's cocked off at an angle to correct the tracking, and then you do it like this. Where the cutter head went straight across the record. It didn't swing. Ideally, if you could go straight across the record, I suppose, with some sort of a reasonable mechanical device, it'd be the best way to do it. But most of the devices that have been designed aren't reasonable. They're really something else. Yeah.
I've seen a new Mitsubishi tape record.
And this is straight arm.
And it looks like a tape recorder. It stands up straight. You put your record on like this, and it has like an arm that comes across here that holds it on. And your playback has to
Just move across, straight across. This is the ideal way to do it, straight across if you can. But it gets to be a complicated thing mechanically. It's simpler to use a arm. Of course, there's a lot of designs for arms. I don't think you can pick up half the AES journals that come out within a year that there aren't several articles on design of arms and design of styluses. And one thing we didn't mention was this screwy angle that you see on the things. If you look at an older phonograph, the way it was built, most of the files came directly down out of the pickup. Yet today, most of them look something like this. And they have an angle that the thing is dropped down with respect to the pickup, the head itself. This turns out to be someplace between 15 and 25 degrees. The reason this exists at all, because we found that there's a distortion that occurs due to the plastic material that the record is cut in. This is called springback. This is where the record itself is plastic. That's this thing right here, which is the master. This is nitrocellulose acetate, and it's sprayed on an aluminum disc. In order to keep from getting too hard, it's allowed to cure in its own atmosphere, where they have the carriers for it, and allow it to, it's like having paint, like painting something, and then keeping a dense atmosphere of the paint fumes in the room, and letting it, and this allows it to come into a fairly soft consistency that can be cut. And we can cut this stuff, but it's still plastic. And being plastic, it has a property that most of you, I'm sure, have seen with plastic. If you bend it, it'll come back. That's what's called spring back. Well, if you're cutting in the plastic also has the same property, wants to spring back. And they found that if the cutting angle to overcome the distortion produced by the spring back in the plastic was made to be somewhere between 15 and 25 degrees, depending on who you are and what numbers you used in your equations and this sort of thing, how you derived your statistics, you could compensate for this distortion and make a correction. Well, we do this in the cutter head. The cutter heads are made to compensate at roughly 20 degrees or 25 degrees for the spring back of the plastic to reduce this distortion. This means now that the the effective angle of the cutting stylus is not straight down. In the Westrex cutter head, looks like this. The stylus is mounted in an arm here, and this is the cutting stylus here. This is fixed back here. Then this plate, in turn, is fixed up at this point. So the cutting angle is really like this. These are tied to the coils we talked about, both up this direction and back out that direction. But the cutting angle turns out to be about 25 degrees. Even though it is cutting across the record straight. Everything looks like it's straight, but actually the fulcrum is up here, which makes it this 25 degrees. Now, in order to play it back properly, what you do is compensate for this and make your stylus look like this when it plays the record. It compensates for the fact that we did the same thing when we recorded it, to compensate for the spring back of the plastic. If the plastic didn't have this property, we wouldn't be doing this. And what you're doing is not to affect, there's no effect of the vinyl itself. It's to compensate what we did when we cut the record. And that's where your playback angle comes in. That's due to spring back of the plastic. Any questions on any of that? Really wild, isn't it? Now, when I say you told us all about all this crazy stuff and everything, now what do you want from me when I get a tape? What can I do to make a better tape for mastering? And some of you may be going to other, how many of you are out of studios? Have you worked in studios somewhere? How many of you musicians? Most of you musicians? Or any of you electronics bugs? Oh, you got some electronics people in here. Well, what we do, I find very useful as a tool to use in determining what the material like that you've got, and I know what to do with it when I'm cutting, is to use an oscilloscope. You've all seen oscilloscopes. You go out and buy a $15 or $20 oscilloscope and junker somewhere out of the hawk shop, somewhere to get rid of, and take the oscilloscope apart and rotate the tube in it. Remember the long tube that lights up green with the lines on it? Rotate the tube 45 degrees so that once you've rotated it, this is the vertical, this is the horizontal. And what I do is feed this vertical now with right information and feed the other input of the scope with the left information. Well, what this causes, the little spot on the scope, when there's no signal at all going in, you just have a little green spot right in the center. And as I turn on the right-hand channel, I see the thing start moving this way. See motion this direction. Shut off the right-hand channel, turn on the left-hand channel, and it moves this way. When I turn them both on, left and right, I see something that looks like this. It's all jumbled up all over. But what I'm really looking for is to see the amount of excursion I have this way, the amount I have this way, and I also see the balance between left and right immediately. With this type of a monitor, you can detect about 1 dB shift or even less in left and right unbalance if something is going in. And it's real useful, particularly where there's a tape that's been mixed over several different days or several different stations. There may be slight changes in the balance, and you can compensate a little bit where you would not normally hear it, but it keeps the record right on. You can also sense with this type of device if you're getting these great big vertical excursions that are going to cause the record to go the needle to jump up off the record, come clear off, because in that case, it's going to get very heavy in here like this. In fact, if the material is mono and in phase, it'll show up as a line like this across the scope in this direction. So you see it, a straight line moving back and across and coming and going. If it's out of phase, if you simply wanted to check, see if something was in or out of phase, it'll look like this, be up and down. And if it's, of course, right information, it looks like this. If it's left, it shows up over here. So what you get is combinations of these in stereo, because there is some things that appear out of phase. And what we'll normally see, and I think you'll see it in the tape, is a thing that's going to look something like this, with its being the green area. It'll look like that, indicating that there's a lot more in phase than there is out of phase. Very simple way to do it. So this is probably the first check we'd make on a tape that you sent to a master.
Would you play
Yeah.
the whole tape through that?
What?
Would you play the whole tape?
Yes, sir. Yes, sir. Mm-hmm. And particularly what I like to have, if you're the engineer doing the job for me, if you can tell me when you mix it, I think in the third cut, the last half, I might have a problem. Things didn't, they didn't go together real well, but we got it mixed. But you ought to take a look at that. Or your loudest thing on this record is the fourth cut. That's the loudest thing on the whole record. But in preference to that, what I'd like to have you do is, if you could, give me tones. Establish tones at the beginning of the tape. And the guys down here, when they're sending me a record up to cut, what they'll do is give me 3 tones usually. They'll usually give me 1,000 cycles for a period of, 20 seconds or so, in left and right channels, balanced equally. That way I can determine what your balance was. They'll also give me 100 cycles, which will give me an idea about equalization, if anything is strange in the equalization. Another thing they'll do is give me 10,000 cycles. 10,000 cycles does 2 things for me. It allows me to check equalization, to see how I am equalized with respect to what they were, and also alignment of the playback head in the tape recorder. Because in proper phase alignment, what will happen if it is not phase aligned properly, I won't have a straight line. I'll have a thing that looks like this. I'll have a circle or an ellipse, which is a portion of the circle. And what I'll do is adjust the azimuth in if you've gone through your maintenance part of the work, you adjust the azimuth, and that's the position of the head like this, with the tape moving this direction. You'd move the head in this direction until the scope no longer looked like an ellipse, but appeared to be a straight line. At this time, I'm aligned with the way his head was when we recorded it. So with those 3 tones, the 1,000 cycles, 100 cycles for low frequencies, and 10,000 cycles for high frequency equalization, and also for azimuth alignment, we can do it. I need to know also if you had noise reduction on it and the type of noise reduction. Dolby has several types that could be on the tape, and so does DBX, and they are not compatible. We need to know if there's noise reduction there and the type of noise reduction. And of course, if it's Dolby, we need Dolby setup tones. If it is DBX, the 1,000 cycles is normally used to set up the DBX system. But we need to know that. Another thing that's very necessary is to let the engineer that's mastering know if you want bands, between songs. Sometimes you don't. And sometimes you may have a tape. For instance, you're producing a recording that you want to sound like it was live. It's a studio recording, but you want to sound live, or it might be a live recording, and it's continuous. There's applause, ambience, and background noise all the time. Well, the engineer doesn't have a crystal ball, and he isn't quite sure where the bands are supposed to be. He might just put them in at random, but I don't think you want that. The best thing is tell him how far in time it would be in that case, or in the case if it's an edited tape where you put white leader between the songs. When you've edited the tape, we know then we'll band there unless we have instructions otherwise. That's the way that is normally handled. Another thing that's very handy, and this has saved many engineers hind end, when he got in trouble. He got the songs on the wrong order, or he left the song off. And if I have a copy of what the record is going to be, the label copy, a lead sheet, I can catch it right then when I'm mastering it. We also catch little things like somebody failed to make an edit. We get it halfway into song cut number 3. Wait, stop. Start that again. And I've had this happen. I expect it half a dozen times, mastering in all the years I've mastered, for somebody didn't get it cut out. Oh, is their face red now? It's almost as red as when they leave a song off or add a song that isn't supposed to be there. And that's why the lead sheet's handy, because this is about the last time it's going to be checked and caught, since we're listening to everything all the way through, and we can catch everything like that. And again, like we mentioned before, if in one of your cuts you've done a live recording somewhere, and he said that as they do sometimes, the vocalist climbs right up into the mic at 150 dB and the mic can't take it, he say that in the fifth cut, the lead singer got into the mic and he distorted. We distorted in the second chorus or something. It got out of hand a little bit. If you let us know that, we know that it isn't something going wrong in our system, because we always suspect that too when something happens. We have a problem somewhere. So if you can tell us of obvious problems that you know of that have occurred, like the singer distorted in the fifth cut, or you might say someplace when I was doing it was a direct 2-track recording, the left channel drops a little bit in the fourth cut. Bring the left channel up, balance it out a little bit for me when you do it. We can do that, but we need to know it. Fourth cut comes up, we'll look for it. Usually what I'll do if I'm mastering, if you tell me that, I'll go in and play the fourth cut before we ever cut it and listen to it and see where it happens. So that's a good idea to know. And anything like that you can tell us, help us. And I'm sure that with your training you've had here that you'll always properly mark your tapes. We have had tapes come in where we did not know the speed, did not know the track configuration. We've even had tapes come in where they have switched speeds in the middle of the tape, where one was at 15, the next one was 7.5. Well, most of the machines won't change speed that fast. You have to allow time for the motor to slow down. Well, you tell me the next cut's at 7.5 and I hit the speed switch, where the motor hasn't slowed down yet. By the time it gets into the cut, we come down into it. Doesn't sound very good. So try to make all your masters at the same speed and with the same head configuration. Don't switch heads in the middle of it. Make one cut with a 4-track stereo head and the next one with a 2-track. Doesn't work very well. Cause a lot of problems. That's about it. That's what you can really do to help us. And yeah.
What if like during cutting the tape itself, speed up the clips a little bit, compensate for something being out of tune? You have to know that.
No, not really. And unless it caused a problem, unless it was an obvious problem to the listener. But usually you'll fix a thing like that, nobody will ever hear it. Never know it. Never know what happened. If you're using Verispeed on something.
Well, yeah, like when we're editing the tapes, is that the amount of pause it's going to have before the next cut?
That's the amount of time pause, but we can control the width of the band, whether the band is very wide or very narrow. We have control over that. Usually a good time's 3 to 4 seconds, something like this in there. Because you want any reverberation or sound you may have to tail off before you cut it. Get it back down, and then this takes a little time, so a 3 or 4 second band normally is adequate. That sort of thing. But that, we can make the band anything you want. Normally, we try to keep them as narrow as we can, because any space we use in banding is not useful space for sound. That means that amount of time has been lost for sound. And we want to keep just as much space as we can for time, but this allows us to make a louder record. Keep the quality higher. Yes. To do what? No, that's all external to the cutting, to the amplifiers and the cutting head itself. The way this is done, you might be interested in that. The way this is done, the lead screw that drives the cutting head across is driven by a separate motor, independent of the motor driving the turntable. And all we have to do is vary the speed of that motor. In fact, ours is set up where we have what we call marginal control. And marginal control is nothing more than a means of sensing the sound level of the tape. And then as it becomes louder and louder and the excursion of the stylus is greater and greater, in the lateral or in the case of the vertical, needs to go deeper, we can drive it in that direction automatically and allow it to either be opened up to allow for a greater groove excursion or increase the depth of the cutting stylus. And there's several techniques to do it. I prefer to do it by what we call preview, where we're listening about 1.5 to 2 revolutions ahead of where it occurs. There are some techniques that say that this can be done almost instantaneously. I don't believe it because of this plastic deformation and distortions that occur. You may be able to get a little more dense on the record, but there's some other sounds and distortions that occur at the same time. We say, what do you mean by distortion. How many of you ever played a record and before the music started, you heard it one revolution before it started?
Yeah. Yes.
It's what's called pre-echo, and it's particularly bad on something that starts very loud. What has happened is that the sound from one groove, because of plastic deformation, the sound is transferred into the adjacent outside groove. This is happening all the time in the record if it's loud too. But the level of the material is so high that you can't hear it. But it's in there and causing some distortions down at lower levels. But what happens there, the way we get around that, is rather than allowing the grooves to come close together at the beginning of the song, rather than this, we open it way out so that the lead-in groove just before the first music note is way out, much wider than it normally would be. Because if we don't do this, I've done a lot of mastering of martial music, marching bands. And everything on a marching band is bang like that when it starts on the first note. Just about everything starts big. Well, without doing this sort of thing, we had a lot of this problem. And I had, commercially, many people do it, but I had to just about double what was being done for a lot of this loud march music in order to get away from this pre-echo. And we stopped it so you don't hear it. And it was simply done by keeping that first groove way off the first music groove and then let it come in after the music started and get rid of the pre-echo. There's also a possibility when you end with a big bang to hear that one revolution later, and that's called post-echo, where it transfers over to the next groove. And the problem is more magnified by the amount of time that this, which is the master we cut, look at that, pass it around, that is what we actually made. The amount of time that it sets before it's played. What is done now in the process to make a phonograph record from that thing? That thing can be played, but you can't manufacture phonograph records from that piece right there. That's called a master. From the master, we take this to a plating facility. We don't do it ourselves because it's a very precise operation. There's one company in New Jersey that does it for most of the majors too. And it's Tracy Val. We have them do it for us. They take this, we send this to them, or take it to them for a big hurry. First thing they do is spray it with silver. The operation looks very much like they're spraying the side of your car. Use a spray gun with silver sensitized after it's washed first and then sprayed with silver. The silver sensitizes it. They take the silver sensitized master and put it in a plating tank with nickels. And they start plating this with nickel, build nickel up on the silver. And once this is done, it gets up to the point that it looks like this. This is what is taken from that. This can be put in the record press. This could be a stamper, or sometimes called a strike-off. You may have seen that in your literature. This could be used as a stamper. But and many times in that process, that is destroyed because the plastic will, the nitrocellulose, the black material, pull off the aluminum, and you couldn't make any more. Well, you might say we need to make some more records. We've got a big seller here. We're going to sell 500,000 of this. And these are only good for about 1,000, 1,500 records. So you're going to have a bunch of these things. Well, we'll go one step further. What we'll do is we will take this. Now we'll spray this with sensitizing material and a release agent so that we can pull it off. And we'll make, since this has the grooves raised, you'll be able to feel that the grooves aren't into this, they're raised. They're just like the negative of a photograph. Feel it on here. See that? We'll make from that, by plating it, another phonograph record. And this is that phonograph record. In fact, this record can be played on a phonograph. And it's called a mother. Next step in the process. You've now created a mother. This is used to make more of those because we can plate this again and make those. So we can make about 25 or 30 or maybe as high as 50. Then we get in the problem where we're going to, this thing will have lost most of its life. We'd either have to master the record again or go one step farther. We will take this, which was made from that, and make another one that looks like that, and that's called a father. It's a 3-step process. So you end up with the case where you had the strike off, the mother, then the father, and then the father is used to make additional mothers from. That's the way the whole system operates. But this you can look at is nickel also, and actually can be played on a turntable. Now you can play that stamper with the raised sections on it, where the sound is now raised rather than into the surface, with a stylus that looks like a V shape. And if you've been to any audio shows around, Stanton will be playing them there with a reverse running turntable. Since it's a negative or a mirror image, the turntable has to run backwards to play that. So rather than rotating clockwise as you look down onto the turntable, it's rotating counterclockwise, and you play that, or this, case of 45. That's what one of 45. And the stylus, well, that looks sort of like this. If you're where this goes up and plugs right into the Stanton cartridge, just like your regular Stanton stylus, except the stylus is manufactured like this, and it was really manufactured by cementing two playback styluses together, and they allow this portion then to ride down over that raised area and play it back. We'll do this a lot of times if we suspect something is being wrong. When these come back to us, if we find that, gee, it looks like it's scratched, or it looks like there may be something strange in there, we'll put it on the reverse running turntable and listen to it. Actually play it. And if it's there, you'll hear it. It'll go up very dramatically. And in fact, we have one of these things that's designed as a repair type stylus that will, if there is a raised area on it where a flaw has occurred in plating, we can reduce it to the point that it's almost an order. Yeah.
Don't you like cover up the grooves, spraying that silver?
No, it's put on very, very thin. Just a molecular, very thin coating, not nearly as heavy as you would paint something. It's just sprayed on enough to sensitize it. The silver is then recovered. It's taken back off again. They reuse it. But the nickel that's it. And of course, nickel is worth $1.13 a pound now, I think.
So, I mean, when you're cutting the master tape, you make the holes, make the grooves a little bigger.
No, they're exactly like they here on the record. The groove geometry is pretty well. There is some loss. I see your point that aren't you going to lose this sort of thing, because that can actually cause a skip where it might not have caused a skip in the master. There is some loss in the process. But it's amazing the fidelity can stay as good as it does with going through that number of steps. And it's gone through a lot of steps just getting to the master electronically, and let's think the number of steps it goes through by the time it gets to that metal plate. Those plates, the first one you saw, is then put in the press. The record press uses vinyl, and the labels are pressed right into the record. Some people think the labels are glued on. They're not. They're pressed right into the plastic material. The labels have to be of the right consistency, the proper paper and the proper ink. If the paper is hydrostatic, takes on moisture, the paper will pull apart the press. And if the inks are a problem, the inks will pull off the paper. There's certain type inks that must be used in making record labels. The plates are heated to about 250 degrees. The record is then molded by squashing the plastic between the records under very high pressure. The record is then pulled out,